Perfect. Let's get started. So in the previous two lectures, we have talked about what is a dynamic decision problem. So a dynamic decision problem is the one where your current action is going to influence the future observation. If it doesn't influence the future observation, it's not a dynamic decision problem. The second thing we learned is there is a notion of a state in a dynamic decision problem, which includes all the information that is relevant for optimizing that process. So it contains information about the cost, it contains information about its future evolution as well, right? And you want to pick the minimal state for a specific dynamic decision problem that you are currently facing. So if you are building a recommendation system for Amazon or building a recommendation system for Netflix, you need to design a state which encompasses the information about the reward, which is whether or not the person who you are recommending to is going to make a purchase or going to watch a video. Alternatively, if you are a doctor and you are coming up with a treatment plan for a cancer patient and you are going to administer drug, you are going to administer chemotherapy, you are going to do nothing, right? So those are the three different actions that you can take, or you can prescribe a specific test. So all of this is a dynamic decision problem, and in this case, you as a doctor are supposed to come up with a state of the health of the patient, and you need to use that information to figure out what is the next drug, next treatment, next chemotherapy, next session, next test, medical test is supposed to happen. There are multiple objectives that you would want to optimize in a dynamic decision problem. You can have a total cost problem where you are there is a finite horizon, and at the end of the horizon you are done. Okay, so I want to optimize my day for the next 24 hours, and at the end of 24 hours I am done with my optimization process. I don't have to optimize again. There is average cost problem where I care about the steady state. So in the average cost problem, you can think about wireless systems, you can think about economy. You care about the steady state, you don't care about, maybe economy depends on the administration. So some administration could be short-term thinking, some could be long-term thinking. So in long-term thinking, you're looking at the average cost problem. In the short-term thinking, you're looking at a discounted cost problem, right? So you care about the transient, you don't care about the steady state. Then you solve a discounted cost problem. And if there is a notion of a terminal state in your optimization problem, then you can use a total cost criterion. So if you know that a patient is going to die of a disease, of a specific disease, then that's the terminal state of the patient. And you want to make sure that you treat the patient in a way that is what is known as a palliative care. So you just want to make sure that the symptoms are managed and the patient feels all right until the terminal state is reached. So that's a total cost problem. You don't know when the horizon is going to end. You don't know when the terminal state is going to be reached. But you know that in the middle, the activity is going to go through multiple states. So in the case of me going back home at the end of the day, that's a total cost problem. I want to get to my home. I don't know whether I'm going to get there in 5 minutes or 15 minutes or 500 minutes. But there is a terminal state, which is me reaching the home, and I'm not going to go anywhere after I reach my home. So therefore, that's the terminal state, and that's a total cost problem. It's not a finite horizon problem. Okay, so one of the things that we talked about in the previous class is the notion of a policy, mu t, which maps the information to action. So this information is the information you have acquired until time t, and this is the action that you need to take at time t. Okay, so we are talking about discrete setting. We don't want to talk about continuous setting in this class, but there is a whole theory of continuous time reinforcement learning as well, but it's something that is less studied and also somewhat less relevant in today's world. Right, so we're looking at the discrete time problem. So I have a policy and that maps the information to action, and whatever cost I come up with, whether it's discounted cost, total cost, average cost, or finite horizon cost, those are all functions of the performance index is a function of the policy that you have picked from time 1 all the way up to time either infinity or capital T, depending on whether it's finite or infinite horizon. Okay, so we also talked about the principle of dynamic program in the previous class, which means that if a policy is optimal, so mu1 to mu t star is optimal, then it has to be optimal for every sub problem starting at time t for every t. And based on that principle of dynamic program that was proposed by Bellman back in 1950s, we came up with a dynamic programming algorithm, which again is a very fundamental algorithm. It's used across many fields and has different names in different fields. So in computer science, if you're talking about graph algorithms, then Dijkstra algorithm is basically the same as dynamic programming algorithm. Okay, so we came up with a dynamic programming algorithm, and where we had the notion of optimal policy and optimal value function. Okay, so value function is the total optimal cost until the end of the horizon. One of the two results that was quite surprising in the previous class was theorem 1. So for every mu history dependent randomized, there exists mu history dependent deterministic such that J mu HR is greater than equal to J mu HD. So if you're using a randomized policy, it's better to use a deterministic policy because you can always beat the cost, the performance index that is achievable with randomized policy. And I'm going to cover the proof of this result in today's class. There is theorem 2 is that for every mu HD, there exists a mu MD such that J mu HD is greater than equal to J mu MD. Okay, so these were the two results that we'll be covering in today's class, after which we'll talk about value iteration algorithm for infinite horizon problems. So let's talk about these two results in the context of finite horizon MDPs. I don't want to talk about the infinite horizon because it just gets into a lot more complications. But the ideas are the same. You use the principle of mathematical induction to prove the results in the infinite horizon case. We'll use that for the finite horizon as well. But you have to be a bit more careful in infinite horizon because you have infinite summation and so on and so forth. Okay, so let's talk about mu star HR. This is the optimal solution, optimal history dependent randomized policy. Okay, so this is given by mu HR1, mu HR2, mu HR capital T. So I have capital T number of policies which maps the history at time t to the action that I'm supposed to take at time t. So let's define U of HT or UT of HT support of mu HRT HT. Everyone knows what support of a probability measure is? Who doesn't know what the support of a probability measure means? Few people? Okay. Sorry? Not just larger than 0. So this is the smallest set for which the probability is 1. Okay, the smallest set. Okay, so you cannot. So support of a set. Just the definition. So I have a probability distribution P. So I have a probability distribution P1 to Pn. This is over this is the probability measure over 1 to n over set 1 to n. So this is the symbol for probability measures in this class. So throughout the course, I'll use delta to denote the set of measures, set of probability measures over a set. So this time the set is 1 to n. The support of P is equal to the set I in 1 to n such that Pi is greater than 0. So that's the definition of support in finite over a finite set, probability measure over a finite set. Over infinite sets, intersection of all set C such that how should I write it? C. This is the intersection over all C such that C is closed and the probability measure over C is equal to 1. So this is the case in when you have when the original set, here I have written set as 1 to n, but you could have infinite set, you could have Rn, you could have a general state space or general action space. So in those cases, this is how you define the support of a probability measure. Until mid-October, we only care about this sort of support. After mid-October, when we talk about continuous state, continuous action problems, then this is the definition of support we will be using. Any question? So it's the smallest set for which the probability is equal to 1. And this by definition is closed. Okay, so support is always closed. Any questions so far?
So the support in the second line, so it's just some index, right? The index you use the second line.
Yeah.
It's just some index.
Just the index. The index I or the elements of the set 1 to n I such that Pi is greater than 0. Okay, so I am looking at this subset of actions at time t and at the history ht, which is in the support of mu of HRT ht. So let's look at the first result. So I pick an optimal history dependent randomized policy. So certainly J of mu HR is greater than equal to J of mu star HR. Now let's think about the value of mu HD capital T evaluated at H capital T, so history at time capital T. Let me define it as min over all U capital T in UT HT of summation Pij U. How should I write it? I capital T plus 1 C I capital T U I capital T plus 1 plus V. The terminal cost was, this is CT plus 1 IT plus 1. Yeah, this is right. And this one turns out to be less than equal to V of mu HR star. Oh, I missed a star here. So this is the optimal policy, and I'm using this for the optimal policy. Okay, so I'll let you guys note down, and I think this is the most important step that we need to understand, because that is going to lead us to the solution. Okay, so I have two. Okay, I'll make sure everyone is noted it down.
Professor, just a quick question. So
Yes.
we are trying to minimize this cost, not
This is the cost. This is the cost problem.
So optimal is minimum. Right?
The optimal is minimum.
Okay.
Yeah. A lot of the times people, this is a very common joke in reinforcement learning community that control is about minimizing cost, reinforcement learning is about maximizing reward. But the way to go between the cost and reward is you take the reward, multiply it by -1, it becomes a cost, right? So you have a maximization problem, you multiply it by -1, now it becomes a minimization problem. Okay, so we are always going to talk about cost, but then there will be times when I will switch to reward depending on what paper I am presenting in the class. Okay, so what is happening here? So when I use the randomized policy, I look at the history HT, and then I am randomizing among different actions. So I might have 5 possible actions, and I'm randomizing among those 5 actions. Now you can have an average cost over 5 different actions, or you pick the best action among those 5 actions. Okay, if you pick the best action, okay, which is a minimizing action, then in that case you will definitely improve the cost to go. Okay, so this is the cost to go, this is the terminal cost, and this is the future cost. So you're definitely improving the cost to go if you use the history dependent randomized policy, and this is the optimal policy that I'm picking. Okay, once again I want to remind you there was a mistake here. I want to use the optimal randomized policy for the support. Okay, so instead of randomizing over 5 actions, I'm going to pick the best action, and I'm definitely going to improve upon the total cost to go for the optimal randomized policy. And this is true for all HT, right? Because HT is completely arbitrary. I've not made any specific use of the properties of HT here. So for any history, I can do this. I can pick. Why am I making so many mistakes? Okay, so this is capital T here. Please make that change. So for any history, I can pick the actions that were in the history dependent policy, randomized policy. I'll pick those actions in the support, and then I can optimize and I can improve upon the cost to go. I can do the same thing let me write it. V mu star Uh, So I pick this and I do again the minimization operation here among the support, and because of this inequality, what I get is this is minimum over mu star HR capital T HT, because I know that this inequality holds. Therefore, this inequality holds, and this is less than equal to V would complete the proof by using the induction.
So just a silly question.
Yeah.
We are assuming the cost function C is bounded, right?
That's right. We are all in a finite state setting right now. Finite state, bounded cost, everything is nice and easy. Okay, so this one holds because I picked the so mu HDT is less than equal to mu HRT, so that's why this particular equation holds. So I can go from here to here with an inequality sign. I can go from this sign, this statement to this statement, because remember in this case I'm randomizing over several actions, whereas here I'm minimizing over the actions in the support over the specific support. So therefore, I'm definitely losing out some optimality because I'm randomizing among multiple actions rather than picking the best possible action. Okay, so I have that if I pick this history dependent policy where I'm taking the argument everywhere, so I'm taking the argument here, putting it in history dependent T, history dependent policy at time T, so that's the argument of this. Same thing here, I pick the argument here and put it in history dependent T minus 1 policy. So I'm storing, what I've done is I started with a history dependent randomized policy, the best history dependent randomized policy, and I've constructed a history dependent deterministic policy that beats the expected cost that you can achieve with the randomized policy. And this is at every time step. So this is at time T, then I prove the same thing for T minus 1. I can prove the same thing for T minus 2 and so on. By principle of mathematical induction, it holds true for all time steps. Okay? As a result of which, I have proved this result, that for every mu HR, for every randomized policy, there is a deterministic policy such that the deterministic policy beats the performance with the randomized policy. And that's because randomizing over bad actions is worse than picking the best action, right? It sounds very obvious, but that's what the result in theorem 1 is. So there's no point of randomizing in the case of a dynamic decision problem unless you are in an adversarial setting. So only in adversarial setting you have to randomize. You know, we are not talking about adversarial setting here. So in the usual setting, you always want to pick a deterministic policy. The second theorem is, for every history dependent deterministic policy, there is a Markov deterministic policy that beats the performance of history dependent policy. And the proof of this result is also on the board. Okay, and let me show you how. Remember that I'm minimizing this objective function. This is a function of it plus 1. So state at time t plus 1. This is a function of state at time t, action, and the future state. I'm averaging over all the future state. So this summation is over it plus 1. Okay, so now the question is, does the optimal policy depend on the entire history or does it depend only on it? So what I have is a situation here. I have a function of I, u, and x. I am minimizing over u. Okay, I have a function of I, u, and x. This function f doesn't depend on x. This function that I'm seeing here, it depends only on it, u. That's it. It doesn't depend on everything else that has happened in the past. Does that make sense? So I look at this objective function. I have averaged it over it plus 1. It's only a function of it and u. And it's not a function of everything that happened until time t, except for it. So I have a function that's a function of it, u, and some information that doesn't really influence the function. Do you think that the argmin is it a function of only it, or would it be also a function of x? So I have some irrelevant information. I'm optimizing a function with irrelevant information. Would the argmin be a function of the irrelevant information? And the answer is no, right? There is no point of using irrelevant information in order to optimize this function. Does that argument make sense? So you have a bunch of spurious random variables. It doesn't really influence the cost function. You're trying to minimize that cost function. So the argmin, which is the optimal policy, is not going to depend on the spurious information that doesn't really matter to the objective function. Okay, so the argmin will be a function of it only. F does not depend on x. So just because I wrote it as a function of x doesn't mean that it depends on the entire x. It only depends on the current state. It doesn't depend on anything that has happened in the past. And therefore, the policy doesn't depend on it. So what I can do is, whenever I'm creating this mu of HDT, I can actually make it mu of just the current state. Right? So wherever I'm doing the argmin, mu MDT it is equal to the argmin of, in this case, ut in capital U. Okay, I can do the argmin over the entire action set, and I can beat the performance. By the same argument, I can beat the performance, and I get that a Markov policy beats the history-dependent deterministic policy, a Markov deterministic policy. So there is no point of randomization, and there is no point of history, okay, in a Markov decision process. No point of randomization, no point of history. So we started with a very big problem. We wanted to optimize this performance index over the entire set of history-dependent randomized policy, and we realized that there is no point of doing that. It only makes sense to optimize over Markov deterministic policies, and we are good to go. Any questions so far? Yes, please.
Theorem. Okay, so why for your argument that you use Markov property, why don't we just use equal? Instead we use greater or equal to?
The reason why I'm using greater than equal to is because there are greater than equal to signs all over the place, so I have to keep track of that. Right? So here, if you think about it, I can't write it as equal to. unless I know that the support contains only the optimal solutions, only the optimal actions. Right? So then again, I'll have to prove the result that the support contains only the optimal actions, and then I'm randomizing among the optimal actions, and therefore any action should be the same. So only that would give me equality. But I want to have a simpler proof, not a complicated proof here. Okay? Any other question? Yes, please.
So theorem 1 and 2 are true specifically for the
Markov decision process. Yeah.
Which are the 4 like
all
those
4.
theorems
All
are
4.
tied to the
Yeah. It's
performances.
all 4 performance index. As long as you have the state of the system and action of the system perfectly figured out, these 2 results would hold, because the state transition depends on the current state and the cost function depends on the current state, right? As is the case here. Cost depends on IT and the P depends on IT and doesn't depend on any of the things in the history.
Are there other performance indices that theorem 1 and 2 wouldn't hold for that are interesting?
I mean, theorem 1 and 2 will not hold for?
Yeah.
Good question. I don't really know. See, typically, when you look at papers that are using history-dependent policies, is because they have not figured out their state space very well. Okay, like I said in the Amazon example, I bought an iron. I'm not going to buy another iron until this iron goes out, which might be in 10 years, 15 years, whatever. Right? But still, Amazon is going to recommend me, like, here is a new iron for you, and it's an irrelevant recommendation, and that's because they are using some history-dependent policy, but they haven't figured out the right state space. That this guy, once a person buys an iron, he or she is not going to buy an iron for another 10 years, right? So that is not part of the state space, and therefore they are giving you wrong suggestions and wrong recommendations. Okay. Now recommendations will never be the same. Now when you go to Netflix and Amazon Prime and so on, you will realize that they are recommending you irrelevant items, and that's because they are using a history-dependent policy and they haven't figured out the state space. Any other question? Okay. Perfect. So these results are from the Putterman's book, page 85 to 90. So in this book, page 85 to 90, these results are proven. Now Putterman book uses reward rather than cost. So I'm talking about cost here, but he talks about reward. So the signs are different and the results, instead of C, he's using R. His state and action spaces are somewhat general, so it's a bit more complicated, but the crux of the argument is what's there on the board. Okay. So one thing that we have figured out is we always have to look at Markov deterministic policies. So we always have to look for mu t, which doesn't map information at time t, but only the state at time t, which maps to action at time t. So now my policy space is much smaller. One of the fundamental questions in Markov decision processes is, under what condition can I find an optimal policy? When does an optimal policy exist? So remember, we have 4 different problem statements. So we have finite horizon, we have in the infinite horizon, we have discounted cost, we have average cost, and we have total cost. Okay, And the question that I'm facing, so remember what we want to do is minimize J of mu. Mu is in Markov deterministic class of policies. I want to solve this problem, and as always is the case in any optimization problem, you want to know if I can achieve the minimum, and how do you compute what mu star looks like. So there are two questions. Is the minimum achieved? And question 2 is how to compute mu star. So this is about existence of an optimal solution. This is about computation of the optimal solution, or one of the optimal solutions of the problem. Okay, let's look at two problems. I want to minimize x square, x is in R. I want to minimize e raised to x, x is in R. What is the minimum here? What's the minimum value of x square? 0. What's the minimum value of e raised to x? Okay, minimum doesn't exist, right? But infimum exists. So let me write it as inf of e raised to x. What is inf of e raised to x? What's the value above which this e raised to x curve lies, and that's the maximum value. That's 0, right? Okay, so infimum exists in both cases. Okay, so infimum here would be actually minimum, but here it would be infimum. What is x star here? Zero. What is x star here? Doesn't exist. So someone comes to you and says that, look, I want to minimize e raised to x, where x lies in the real line. The first thing that you have to think about, is the minimum achieved? Are we really achieving the minimum, or is it just an infimum? And if I am able to achieve the minimum, how do I compute x star? So in this case, there is no minimum achieved, right? And there is no question of finding an x star. There is no x star. Okay, so why do we even bother about trying to find what x star is in this setting? On the other hand, in this case, a minimum exists, and then I can use some tools from optimization, which is ECE 5500, that is concurrently running in this semester. How do I solve this problem and figure out that, okay, x star is actually equal to 0? So these are the two questions that we care about even in this setting, except that now this setting is way more complicated than this setting. Okay. A lot of these problems were studied from 1950s to 1990s roughly. And by 1990s, 1995, the theory was kind of sort of solidified. There have been some developments since then on proving whether or not a minimum is achieved and how do we compute mu star. But more or less, we'll be covering the theory that was developed until 1995 in this class. Okay. So one of the things that I had brushed under so far, and I'm going to bring it up again, I'm going to assume that my state space is finite, action space is finite. Then the answer to these two questions will be very simple and straightforward. For continuous state, continuous action setting, I'm going to defer those results to, I don't know, mid-October or end of October. Okay, so we'll come back to this for continuous state, continuous action setting in the future. Okay, so what do I have? Finite state space. Finite action space. Bounded cost. And then general So this is known as transition kernel, transition probability matrix. You know, there are many names depending on the book/reference that you are reading. Of course, in the finite state, finite action setting, everything can be viewed as a matrix. So therefore, transition matrix seems like an appropriate term to use. But I'm using the term kernel purely because in the future, we'll be talking about continuous state, continuous action setting as well. Okay, so we'll start with a general transition kernel, and then we'll start putting more structure onto the transition kernel in order to make sure that we can also talk about average cost problem and total cost problem. So there are some restrictions on the transition kernel for average cost and total cost, which we'll cover in the subsequent classes. Okay, any questions so far? Okay, so we have a finite state space, so there are only finitely many states that are possible. There are finitely many movies, there are finitely many items on Amazon, there are finitely many items in Kroger. So that's a finite state space. We have a finite action space. There are only so many movies I can recommend. There are only so many items I can buy in a day. So that's a finite action space setting. I have a bounded cost. There is finite amount of money I have, and that's all I can spend. And every item has a finite price. There are some things money can't buy, but for everything else we have MasterCard, right? So things that you can buy, there is a bounded price for it, right? So that's the bounded cost situation. And we have a general transition kernel. One thing that I did not cover in the class in the previous lecture, but I want to introduce it today, we have a state dependent action set. U of S, which is a subset of U. So if I'm at state S, I'm using S. Let me use I, because so far I've been using I for state. So I'm at state I. Then there is only a subset of actions that I can take. So if I'm driving my vehicle at 40 miles an hour, I can only shift the gear up by 1 or shift the gear down by 1. I can't really go to whatever gear I want to at that particular speed. If there is a traffic light in front of me and the traffic light is red, okay, what is the action that you are supposed to take? You have to decelerate. You have to stop the vehicle, right? So if the traffic light is red and that's your state, you have to decelerate. That's the only action available to you. You can't accelerate. On the other hand, if the traffic light is green, you can coast or you can accelerate, right? Those are the two actions available. Of course, you can also decelerate if the traffic light is green, that's fine, but So there are 3 actions available when the traffic light is green, but only 1 action available when the traffic light is red. Okay, so that's the state dependent action set. You look at the state, and based on the state, there is only a few actions that are available to you. You can't really take any action you wanted at that particular state. So remember when we were talking about the state space of a system, this is the additional thing that you need to make sure that the state encompasses information about what actions are available to you and what actions are not available to you. All right, so let's talk about the finite horizon problem. Now that we have solved the first mystery, which is we don't have to look at the history, we can just look at the current state. We use the Bellman's principle of optimality to come up with an algorithm that computes mu star in that case, but let's look at each and every step and make sure that those steps are fine. So I have Vt minus 1, or Vt of It is min over u in capital U of It. So I'm only taking the actions that are possible at the state It, summation It plus 1 Pit It plus 1 u C capital T. Okay, that was the last step, and the mu star is the argmin of the same equation. Okay, so this comes from the Bellman's principle of optimality, which we covered in the previous class. So we look at only the final step problem. I look at the sub problem starting at capital T, and I'm trying to optimize the action at that particular time, and I store the optimal action in the policy at It, and I store the optimal value in Vt at It.
Just a quick question. The
Yes.
minimum here and also the minimum used in the proof of theorem 1, theorem 2
Yes.
relies on the finite action space.
Finite action space. If you have infinite, then you want to make sure you are solving an x square problem and not e raised to x problem. Okay, so that's why.
Key assumption here, finite action space, right?
Until mid-October, that's the key assumption. After mid-October, then we'll go to more esoteric spaces.
Oh, thank you.
Yeah. Okay. So now I have a finite set of actions. So remember, this was finite action set. I have picked a subset of a finite action set, so that's a finite action set. Can I minimize a bounded? So this is a bounded cost, something between 0 and 1. So this is a bounded cost. So I'm minimizing a bunch of bounded values over a finite set. Does the minimum exist over a finite set? Yes, it does exist. So value function is fine. Can I find the argmin? Yes, I can find the argmin. So mu star there is a value at which this particular optimal value will be achieved. There is an action for which this optimal value will be achieved. So mu star exists. Okay, so Vt exists and mu star T exists. What about the value function Vt? So Vt is also bounded, right? Vt is bounded by two times the infinity norm of C, the cost function. So whatever is the maximum value for this cost function and the maximum value for this cost function. So the value function will always be less than equal to 2C infinity. So this is also bounded. So the value function is also bounded. So Vt exists, mu star T exists. Vt is bounded. I can do the same thing at time t minus 1. So let me write the expression at t minus 1. Okay, there's a whole bunch of arguments here. Don't want to write the arguments. But again, I have a bunch of finite values. I'm optimizing over those finite values over a finite set. So the minimum exists and the mu star t exists. So if I apply the principle of mathematical induction, at every point of time my value exists and my mu star exists. So the answer to this question 1 and question 2 is affirmative in the case of finite state, finite action, bounded cost, general transition matrix, and state dependent action set assumptions. Okay, so let me write it here. Ui is a subset of U. Okay, any questions so far? Okay, so for the finite horizon setting that I was at, under these assumptions, the value function and the optimal policy exists. Okay, so I can solve this particular problem. I can. Question 1 is also true. Is the minimum achieved? Yes. Question 2 is about computation of mu star, and that we have an algorithm to do that. Yes, please.
We didn't use the state-dependent action set assumption.
The fact is that if you are if your state is finite and you're doing minimization, you don't have any measurability issue. If your state is continuous, you're doing this minimization, then you have to make sure that everything is measurable and so on.
But we had the finite action space. So
Finite action space you can always minimize over a finite set, so that's easy. Okay, so I'm brushing a lot of things under the carpet right now by making finite state, finite action assumption. When we go to continuous state, continuous action assumption, we want to be able to come up with hypothesis on this so that this minimum is well defined and you can actually achieve that minimum. So that's where the complexity comes from, and I don't want to get into it right now. Any other question? Okay, wonderful. Let's talk about the discounted cost next. Okay, let's talk about discounted cost problem. So finite horizon done. I want to remind you what the discounted cost looks like. So J of mu is equal to expected value of summation t equals 0 to infinity C. Did I use alpha or gamma? Can somebody check the notes? Alpha? Okay. Alpha rose to TC IT UT IT plus 1. So this is what I want to minimize by picking an appropriate policy mu. Okay, that's so now the question is, how can I apply this backward induction argument that we did at for the finite horizon case? So let's think about it. So I'm going from time 0 to infinity. There is no terminal cost here because remember I'm discounting, so I care about the transient performance. I don't care about what happens at time t equals to infinity. So how should I go about solving this problem? So the way to solve this problem, the way to find the optimal solution is through what is known as a value iteration algorithm. So I define my V0 to be equals to 0. You can pick whatever number you want, but my initial value function is identically 0 function. And my V1 or I'm going to use k plus 1 equals to tvk, where t is known as the Bellman operator. And it is defined as follows. Bellman operator T that maps value function space to value function space. Where V is the space of all functions from S to R, which is the same as R raised to S. So you can think of it as a vector, V as a vector. So V of S1, V of S2, V of S3. Remember, we are in a finite state setting. So I can think of the value function space as a vector. So this is V of S1. Okay, this one is not time. Okay, so I just want to make a comment here. Well, I1, I2, In. Okay, so this is not time index. This is just the index of the number of states. So I1, I2, In, these are the states. These are the finite states in the state space. And so you can think of V as just a vector of n dimensions, because there are n states in the system. Okay. So I'm going to define a Bellman operator that takes as input a vector of this form and outputs another vector of this form. So TV of I is given by min of U in UI and this summation is over all j. This alpha is the discount factor. This is the same alpha that I'm using here in alpha raised to t. Okay. So in order to solve this problem, discounted cost problem, I have to use what is known as a value iteration algorithm. So how do I initialize the value iteration algorithm? Initially, my value functions are all 0. So I pick a 0 vector in this particular space. Then I apply this Bellman operator that gives me another value function. So I come up with an iteration vk plus 1 equals to tvk, k is greater than equal to 0. So v1 is tv0, v2 is tv1, and so on and so forth. What is this Bellman operator thing? So the Bellman operator gives you a new value function. Let me call it v bar of I. So this tv is another value function which, evaluated at I, is the expected future cost starting with I, where I'm taking all the actions that are possible at the state I. So I'm minimizing over all such actions of the expected future cost. But remember, this value function gets discounted by the discount factor alpha and recall that alpha is between 0 and 1. Okay, so the discount factor is between 0 and 1. If your alpha is close to 0, it means that you don't care about the future value at all. If your alpha is close to 1, it means that you care about the future value quite a lot, right? And then there is everything in between. Okay, so every time I implement this Bellman operator, I get a new value function. And once I get the new value function, I implement the Bellman operator all over again, and I get a new value function, then implement the Bellman operator, and so on. What do you think will happen to this iteration? What's going to happen? Would it converge? Would it not converge? It's a recursive implementation in MATLAB or Python. Would it go to infinity? Would all these value functions go to infinity, or will this go to some stable numbers? And after that, it will not change. Yes?
It will go to a stable number.
Why would it go to a stable number?
Because you keep multiplying alpha by your previous value, which is less than 1, so it's just going to keep decreasing and decreasing.
That's right, exactly. Okay, so that's one of the main results of this methodology, value iteration algorithm, that value iteration will always converge. Remember, I'm making these assumptions: finite state, finite action, bounded cost, general transition matrix, and state dependent action set. So it turns out that this iteration will always converge. Vk converges to V star, and V star is optimal. Okay, so that's one of the main results of the value iteration algorithm, which is that this particular algorithm always converges to V star. It always converges to a value. Turns out that that particular value is optimal, and the argmin at V star is the optimal policy. The another thing that you will notice is that the optimal policy actually doesn't depend on time. Okay, so the optimal policy is always stationary in the discounted cost setting. I'm thinking whether to, well, let me not come up with another operator. So let's say mu star of I equals to argmin u in ui of the same thing. You just have alpha V star j in the end. So you pick this V star that is optimal, that this thing converges to, and you look at the argmin, and that gives you the optimal policy mu star. Okay. Why is this true? We'll talk about Banach contraction mapping theorem next in order to prove this particular result. So those of you who have taken ECE 5500 would recognize this result because we covered it in 5500 as well. But how many of you, I mean, I don't see many familiar faces here, so probably you have not taken 5500. So how many of you know about this theorem, contraction mapping theorem? One person. How many of you don't know about contraction mapping theorem, have not seen this before? Many people? Okay, wonderful. So this is the main takeaway from this particular class. Contraction mapping theorem is one of the major results in the theory of what is known as functional analysis. So I have an operator, I have a function f which maps something from Rn to Rn, and I have a norm on Rn. It could be any norm. It could be infinity norm, it could be L1 norm, it could be L2 norm, it could be weighted sup norm, it could be weighted LP norm. I don't care. It is some norm in Rn. It satisfies all the conditions for being a norm on Rn. And what this function f satisfies is f of x1 minus f of x2. If you look at the norm, so remember f of x1 itself is a vector, f of x2 itself is a vector in the same space. So I subtract these two vectors, take the norm. It turns out to be less than equal to alpha times x1 minus x2, where alpha is something less than 1. Alpha is between 0 and 1, 0 included, but 1 is not included. Okay? So 1 is not included. Alpha has to be strictly less than 1. The theorem, the contraction mapping theorem is, if you define xk plus 1 equals to f of xk, then xk converges to x bar and f of x bar equals to x bar. Okay. So I have picked this. So what is the situation again? My f is a contraction map. This is known as a contraction map. So f is a contraction map if it satisfies this particular condition. So f of x1 minus x2, f of x2 is less than equal to alpha times x1 minus x2. So if this is the case and I start with any initial condition, it doesn't matter what that initial condition is. I run this iteration, xk plus 1 equals to f of xk. Then this xk will converge to some stationary value, x bar. There will be a convergence. And furthermore, x bar is going to satisfy this fixed point condition. So this is known as fixed point. Fixed point of f fixed point of f, and this is a unique fixed point of f. So x bar is unique. So contraction mapping theorem, because this is a contraction map, right? And the theorem says that this iteration will always converge to x bar, which will be the unique fixed point of the function f, right? And what you are essentially able to do is, no matter how you run the iteration, no matter what your initial condition is, you always converge to the unique fixed point of f. Okay? Why is this result important? Yeah.
So if you're assuming that the contraction map exists, then
this holds. Yeah, definitely. Okay, so we run a lot of simulations, right? So a lot of graduate students and a lot of industry professionals are running simulations. You are running CFD simulations, so computational fluid dynamics simulations. You're solving ODEs using, I don't know, ODE 45 or whatever ODE solver you are using. You're solving optimization problems and you are trying to get to the optimal solution. Why do you always get a solution, right? So you run an algorithm, you get some solution, and you say, oh, look, this solution seems to satisfy all the conditions, therefore it's the solution to the problem I'm trying to solve. It turns out that in almost all of those situations, your simulator is actually simulating a contraction map. Okay, almost all the situations. So I'm really making a very strong statement here. Whenever you are running a simulation on a computer and it seems to converge to a solution, and no matter how you initialize, it converges to that solution, it's because you are simulating a contraction map on your computer, and you're essentially using this theorem in order to show that whatever your algorithm converges to is the solution that you are looking for. Okay? So that's why this result is very important, and it comes up in millions of fields that people study because it's a very, very fundamental result, and it seems to be very useful, especially when you're doing computer simulation based things. So even if you're solving PDEs, even if you're solving ODEs, you're essentially using some result of this type in the background. Okay, any question on the contraction mapping theorem? Yes.
Do we have to solve for if the contraction map exists, there always exists a fixed point?
That's right.
Okay, we don't need to assume it exists. It will.
No, this is given. The function f is given. The contraction map is given.
It will always, if contraction map exists,
Yes.
fixed point always
Exists.
And it is unique.
That's right. It is unique. And this is the algorithm. This is the way to get to the fixed point.
Okay.
So you get an algorithm to get to the fixed point. You get the existence of fixed point as long as this contraction mapping condition is satisfied. So all of that happens for free.
The space of the contraction mapping, it's all it needs to satisfy is just this Cauchy-Schwarz kind of this equality.
Yeah, this is not Cauchy-Schwarz, but yeah, it should satisfy this particular inequality. That's what is the definition of a contraction map. Okay, f is a contraction map if and only if this condition is satisfied. Okay, for any norm, I mean there has to be a norm. So if you change the function f, you might have to change the norm as well. Okay, so it's not needed that it has to be L2 norm. It could be any norm, but as long as there is a norm under which the function f is a contraction, then it will always converge. Many a times the beauty is not in identifying the function f, but in identifying the norm over which it's a contraction. Okay, so you could have a function that's not a contraction with respect to one norm, but becomes a contraction with respect to some other norm, as a result of which this will always converge to x bar, which is the fixed point of f. Okay. Any other question? So I have two options. I have about 8 minutes and I have two options. Option one is to go over the proof of this result, which is very simple and straightforward. Option two, actually in order to prove that result, I need to make sure that everyone understands what a Cauchy sequence is. How many of you know Cauchy sequence? How many of you don't know Cauchy sequence? Many people don't know Cauchy sequence. So in that case, I'm not going to cover the proof of this class because it requires you to know what a Cauchy sequence is. Can I take that as given? Can I take that as something that we all agree that it is correct without proving? Perfect. Okay. So I want to use this result. There is element of that result to be applied here because I have an iterative algorithm. I have a Bellman operator. It is iteratively being applied to Vk. The result seems to suggest that this iteration is converging to V star and V star is optimal. So all I have to figure out is a norm. All I have to figure out is a norm under which T is a contraction. Okay? As soon as I figure out a norm over which T is a contraction, by invoking Banach contraction mapping theorem, I can prove that Vk converges to V star. V star is optimal is still not true, right? So that's still something we need to figure out, we need to prove. And then we need to prove that the argmin is the optimal solution. Okay, so this is unknown, but at least this part is something I can prove just by identifying a norm on Rn such that the Bellman operator is a contraction. And the answer is that if you take the sup norm, L infinity norm over Rn, so remember the value function space is basically something like an Rn. So if I pick the infinity norm over V, So if this is my norm over the value function space, then T V1 minus T V2 is less than equal to V1 minus V2. Let me denote it by infinity norm, because I want to make sure that you understand this is an infinity norm and not just a regular 2 norm. So Bellman map is a contraction with a contraction coefficient alpha, which is the same as the discount factor. So remember, discount factor was between 0 and 1, right? So this is a contraction. T is a contraction map under the infinity norm with a contraction coefficient alpha. Consequently, this particular result holds by Banach contraction mapping theorem. Any questions so far? Yes, please.
If the T is a functional mapping, then can we still prove using?
Yes, yes. Because remember, this is still Rn. This is still Rn. It's not something beyond Rn. Okay.
We assume the continuous state space then.
We'll talk about continuous state space when we reach there. It's a long way to continuous state space. Okay. So far we are looking into finite state setting. The value function space is the same as Rn. I can put infinity norm on Rn, and I can make the Bellman operator. I can prove that the Bellman operator is a contraction under infinity norm. So the fact that Bellman operator is a contraction under infinity norm is something that's a homework assignment for you. I will try to cover it in the class or give you the hint in the class so that you can go back and complete the proof at home. So what I'm going to do in the next class is I'll prove that T is a I'll give you hints on why T is a contraction with respect to infinity norm. So as a result of which this result would hold. Then I'll prove why V star is optimal, and then I'll prove that mu star I is indeed the optimal solution. As a result of which we will have existence of the optimal solution, and we'll have the computational method to compute the optimal solution as a byproduct, right? Perfect. So let's talk about the discounted cost problem in the next class. Then we'll talk about average cost, and then I'll talk about total cost. And in average cost and total cost, I won't consider general transition kernel. Okay, I'm going to restrict the space of transition kernels so as to prove that solution exists. Thank you so much. See you on Friday. On Thursday.